All right, well, hey, welcome to another lovely day here in modern physics world. Today's plan, we're going to keep talking Schrodinger's equation. We're going to look at applying it to other situations because like right now, we really only applied it to that one, the particle in the box where we're like, look, the particle's trapped in here. We know it's in here. There's no potential energy. It's impossible for it to go elsewhere. So we solved it, and we saw that we definitely got a wave, and we saw the different allowable energy levels and wavelengths and all that kind of stuff. Well, we're gonna do the same thing, but we're gonna like start tweaking it. We're gonna go with the, well, what if it's in a box, but it's possible for it to escape the box, right? Or what if it's not in a box, but maybe there's just some sort of a barrier that it has to get past, some sort of a potential energy barrier. So we'll just start kind of tweaking it. We'll just keep doing the math, and we'll see what that does in terms of um, the location of these objects when they're waves. And just like we kind of got into that weird thing with Schrodinger's cat of, well, it's alive and dead at the same time. Well, we're going to have particles that are inside of the box and outside of the box at the same time, or at least until they're measured, and then we'll know which side of the box they're on. Or there's a barrier. Is it on one side of the barrier, on the other side of the barrier? Is it inside the barrier? We'll run the numbers. So this ends up being very mathy. It's all probabilities, but it definitely explains a lot of what we see actually occur out there in the real world. So that's my plan. But of course, before we dive into that, let me open up to you guys. Any questions on the homework? I think is there homework due tonight, or is it Thursday?
Let's do Thursday.
Thursday. Okay. So you might not have any questions yet, but let me open it up to you guys. Anything you want to talk about?
I mean, I have a quick question about what we're about to talk about.
Okay.
Are we still doing time independent?
We are still going to be looking at time independent. So this is at a snapshot moment in time, where might the particle be? So yeah, we're still going to be doing time independent. Everything we do in here is going to be time independent. So, all right, any other questions? Nope. All right, that works for me. I'm sure you guys will have them come next time, so we'll tackle them then. All right, so let me go ahead and pop up my whiteboard, and we will start chatting a bit. But let me remind you about Schrodinger's equation. All right, so what do you guys remember about it? Anything?
It's a differential equation.
Okay, it is a differential equation. What order?
Second, and it's linear.
Okay, so it was second order and it was linear. And our variable is that psi, that sort of like trident-y looking thing. But here's what it looks like. So the coefficient on the double prime is this. So we get the negative h slash over 2m. And then we had the second derivative of the wave function. And then we add on to that U times psi, so potential energy times psi, and that equals E times psi. All right, and remember what psi is. This is the wave function. And it's the thing where psi squared gives us the probability. Right, so that square of psi is going to give us the probability of finding the object at any specific location. Right, but this is the generic, what it looks like. And this was built to try to match what they were seeing experimentally, and it ends up working really, really well. So that's Schrodinger's equation. And last time we looked at a particle that was in a box. So what I love is that this is actually the name of this is particle in a box. It's not that I made that up. I think any book you look in, you will see it called the particle in a box. And in that circumstance, what we had, if we were to look at, say, a graph here, that box had a given width, so say 0 to L. And if this is a graph of potential energy versus position, we saw that between 0 and L, the potential energy was 0. And then it basically just jumps straight up. And I'm going to put just arrows here because on either side, we had basically infinite potential energy. So basically, the way to think about this is that if there's an infinite amount of potential energy here, you would need to increase the energy of this particle by infinity for it to get out to the other side. So in essence, the particle is trapped in the box. All right, so another name that we have for this, because you'll see this when you're reading, and I'll probably mention this word or phrase. We call this a potential well, because you think about like a water well where you drill a hole to get to the water. This kind of looks like that, right? And this potential well, we would say, is actually an infinite potential well. Right. So anyway, so we had particle in the box, and what we saw was that for the particle in the box, we got just some very specific forms for psi. Excuse me, where they were all sinusoidal, but they had to match so that they were 0 at the endpoints. And so let me just draw a couple of the different waveforms we saw. We saw the one that was just the half a wavelength in between. We saw another one that was a whole wavelength in between. I'll do a third one here that was 1.5 wavelengths, right? But we had some really some significant restrictions on what kind of wavelengths we could have. And we saw from that, when we kind of ran the numbers on it, we saw all the different possible energy levels. And they were pi squared h/squared over 2ml squared times n squared. So this first bit, you can kind of think of that as just the fundamental chunk of energy. But the energies that this could have on the inside were squares times that. So 1 of them, 4 of them, 9 of them, 16 of them, and so on and so forth. So we already went through this. I don't want to rehash the derivation. But if you go back and you look at your notes or watch the video from last time, you know, we got here with these were the different energies that you could get.
N was the different number of wavelengths, correct?
Sorry, which was N?
N, yeah.
Yeah, so N was corresponded to how many of these things we got. Yeah, exactly. Because like the base case, we had 1/2 a wavelength was equal to L. The next one we had 1 wavelength was equal to L, and then we got 1.5 wavelengths was equal to L. And so if we simplified that, that's where that N came in. The number of wavelengths was a multiple of, was it 2/3 or 3/2? I don't remember, one of those. But yes, that's where that N came from, was which of these states are we in? So think about this from like a probability standpoint, because we didn't actually look at that probabilistically. But suppose we just looked at psi squared. Now, let me draw another graph over here. That's going to be, again, here's our x. But this is going to be probability. So this is going to be the probability that we actually see the particle somewhere between, say, 0 and L. So I'm going to color code them to go with the three that we got here. So red is going to be the fundamental case, the n equals 1 case. So we're going to get a probability of 0 outside of the box. And then you're going to get something that looks like this, give or take. Let me try to make that a little bit better. That was not better. I'm going to quit while I'm ahead. All right, so that would be squaring the red. So most likely in this ground state, that's what we call n equal 1. We call it the ground state. In the ground state, you're much more likely to find that particle somewhere in the middle of the box. Right? The higher this is, the more probability it is in that region. But remember that the probability is an area under here. So the probability that it's at exactly one place is 0. But the probability that we're within an interval would be the area under it. So obviously, it's much more likely that it's somewhere in the middle. Now, if we go to the green one, you're going to actually get 2 peaks in its probability. Because when we square this, remember the negative goes positive. So even this sort of negative area location, when squared, turns positive. And in fact, at the center, I know it doesn't look very symmetric on my graph, but at the center, this wave function is at 0 in the middle of this box. So 0 squared, of course, is 0. So it comes back down here. So in that next state up from ground state, so the next energized state, so that would be 4 times this E. The most likely locations are actually kind of at the quarters of the box, 1/4 of the way through and 3/4 of the way through. If we go to the yellow one, we're going to get 3 peaks. That's going to look like that. But notice that those peaks keep getting lower. And that wasn't just a byproduct of me drawing and being how I am, but they actually are going to get lower. Can you see why those have to get lower?
The distance is increased.
Okay, so
Like
the distance is increased.
travel. Yeah.
But also just think about probabilities. What do you know about the total probability? What's it going to equal always?
1.
1. So we need the total area under this curve to be 1. And so we're kind of redistributing it. That's causing them to go down a bit. Now, let's get to super high energy state. So I don't know what energy state this is, but I don't really care. But let's think about what it's going to look like. So it's 0 until we reach here, and then 0 once we go on. Now, if it's super high energy state, this thing is very wavy, right? Lots and lots and lots and lots and lots of wavelengths. Each one of those, when we square, gives us a peak. So what we're going to see is something that looks like this. So think about what this means in terms of probability. Where is it most likely to be seen?
Probably not at all, or at least very low.
Okay, so the probability of any one place is now going to be very low, but it's almost to the point where everything has equal probability, right? It's starting to look like that kind of probability. It's what we call uniformly distributed, uniform distribution. So if we get to one of these really big ends, there isn't a preferred spot for this object to be due to its wave nature. And that's actually a good thing. I think we actually ran the numbers and figured out what kind of end we would need for like a baseball in, between home and first or something like that, or home plate and the pitcher's mound. And remember, we found that n was like incredibly large. It was like 10 to the 34 or something insane. So what that means is that the wave nature isn't defining where that baseball is, which is exactly what we need, because we don't see the wave nature. It's not like all of a sudden we see that baseball blink somewhere else, right? So what's really nice, even with this model, is as we start getting into the non-quantum world and the non-quantized world, it still applies. It still totally works for what we see because our n values are so incredibly large. But when we start talking about electrons in an atom, we start getting into this world where no, there are just some specific places where it's likely to be. And for those of you that have taken your chemistry, and I always look at Bradley because I know he's the only one I know took chemistry. The rest of you may have, but think about that when you talked about the shells, right, for the electrons. It was always like, well, we don't know exactly where they are, but they're probably here. Well, those probably here's came from Schrodinger's equation. And applying this same idea to an electron in an atom and using the potential energy from the atomic forces to build it. Right? And we will talk a little bit about that. We'll talk about a hydrogen atom just because it's easy. We're not going to go into a lot of detail because this isn't chemistry class, but we'll at least talk about how Schrodinger's Schrodinger's equation, excuse me, led to the idea of the electron shells and the shapes of them, and where the most likely occurrence or location of an electron is. Okay, so this is where we were, but if we look at it from a probability standpoint, it starts showing you where things are likely to be. All right, so here's what we're going to do. We're going to adjust this particle in a box just ever so slightly. We're still going to have a potential.
I got a quick question for you.
Yeah, go for it. Yeah.
So, would a dipole moment give us more evidence to where it could be, or is that itself a probability of when that dipole moment will happen?
It's all probabilistic.
Okay.
But it does, like, just like anything, the more information you have, the more it will tell you about other stuff. But it's still going to be probabilistic. Will there be it's going to be more likely in different places? Yes, there will be a difference. But like you said, there's also the probability of the dipole moment even being there and whatnot. But it's all, you can take any circumstance that you've been in before when you've been talking about it in math or sorry, in physics or chemistry or wherever. And if you look at it through the lens of Schrodinger's equation, it's still going to match up to what you saw, but it will really explain why you're seeing what you're seeing, if that makes sense. All right, so here's what we're going to do. We're still going to have this particle in the box, but this time I'm not going to make it so that the U is infinite outside of the box. We're going to have a finite U. So what this means is now the particle that's in the box can't actually get out of the box. Right? Let's just attach some numbers on it. Let's say U was 100 joules. It's possible that we get enough energy that we can overcome that 100 joules of potential energy and be gone. A great example of this in the macroscopic world is escape velocity. Like, think about gravitational potential energy. It is possible to put enough energy in an object for it to escape the bounds of Earth's gravitational potential energy. We do it all the time when we send things to Mars or the Voyagers out into interstellar space or whatever, right? So that's kind of the scenario. This is more real life. It's not that things are trapped. There are very few places in the universe where stuff is trapped. I can only think of one. Black holes.
Same. Yeah.
Right? You get inside of a black hole, well, yeah, you're toast. Because the amount of energy that you have to overcome is going to require traveling at greater than the speed of light. Sorry, you're done, right? But beyond that, like I'd say a black hole is the ultimate particle in a box. But beyond that, this is what it actually looks like. There's a finite potential energy outside. Okay, so when we do this, we actually have to break this into a couple of different pieces when we look at Schrodinger's equation. Because if you think about it, inside the box, again, somewhere in here, we've got u equals 0. And so if u is equal to 0, that means that our differential equation looks like this. And that's the one that we already solved. It's the one that leads to sines and cosines, gives us some sort of a wave in here. Now, on the other two pieces, let's come out here, and I'm going to say that u is equal to u naught. So u naught is the amount of potential energy that that's being exerted on the particle if it's out here. Okay, well, now that's going to make this differential equation this right here. We're going to have u naught times psi still in there. So the beautiful thing about this is that it's still the same kind of differential equation. It's still linear second order. Right? Because I can move that e over here just like I did before, but I'm subtracting it from the u. And so this is going to lead to a different solution, but a solution that's the same type. Right? Well, potentially the same type. It's actually all going to depend on this u naught minus e. And specifically, it's going to matter what sign that is, plus or minus. Do you see why it matters, the sign?
Yeah, because it'll tell you whether or not the box inside the box had more energy versus the outside.
Okay,
right?
So it is going to be a measure of how much energy we've got in our particle compared to what we need on the outside. But specifically think differential equations. What's going to be the difference if this is positive or this is negative?
It's going to be either complex or not.
Okay. So we're either going to get too complex, which means it's going to look just like it did on the inside where it's some sort of sinusoidal thing, just it's going to have a different, period, amplitude, whatever. Or if it's, in this case, positive, then we're going to get two real roots. What is the solution going to look like if we get two real roots?
It's going to be exponential.
Yeah, it's going to be exponential. Okay, so let's kind of take a look at that U naught minus E and see if we can figure out positive, negative, or whatever. Okay, so E is the amount of energy in our particle. And let's actually start with the, well, let's just kind of break down the difference. So if U naught minus E is greater than 0, so that's positive, then this thing is going to lead to exponential solutions. And if U naught minus E is negative, it's going to lead to sinusoidal. So let's think about what that means in terms of this situation. So if U naught minus E is less than 0, that suggests that U naught is greater than E. So that means that the amount of potential energy you need to be existing out here or to get outside the box is more than the energy that's actually in the particle. Right. So the particle just, it doesn't have enough energy to get outside the box is basically what that's saying. For the second one, this gets reversed. And so now we're saying that the particle has more energy than needed to escape the box. So let's start with that second one, because I think that makes a lot more sense. So if we've got a really energetic particle, more energy than the potential energy that's kind of trapping it, what we're going to see for its wave function outside the box is a wave, just like inside the box. It will have a different amplitude and stuff like that, right? But what we're going to see outside there is business like usual. And that should make sense. If we've got this particle and it's got enough energy to get outside the box, is it going to show up outside of the box? Possibly. Is it going to show up inside the box? Yeah, sure. But what we're going to see outside the box looks a lot like inside the box. Because, all right, if it gets outside, it's outside. It's going to have less energy because it had to use some of it to escape. But we're still going to see sinusoidal. So that should totally make sense. That if it's got enough energy, more energy than the energy that's holding it in, it's possible for that particle to get outside. Yeah, totally. But it's the other one. This is the one that's kind of interesting. So think about this scenario. Okay, so now we're talking about we have a energy level that's less than what we need to get out. And yet we're still going to get exponential solutions to this. They are going to be negative exponential. But let me draw for you the probability function. So this in red is going to be psi squared for this case right here. Okay. What we're going to see is outside of the box, it's not 0. It's a decaying exponential. Inside the box, we're going to see the same kind of thing, depending upon what energy level we're in, right? Increase the N, it's going to change a bit. But this is what we're going to see for probabilities. So just like before, there are going to be places where it's most likely to occur, places where it's least likely to occur. But really what I want to draw your attention to is outside the box. look in these two areas. Notice that there is non-zero probability that it's outside of the box. So think about what this is saying. We do not have enough energy to escape the box. The energy level is less than this potential energy. And yet, there is a non-zero probability that the object is actually outside of the box. Well, that's unheard of in classical physics.
Yeah, I was about to say that doesn't make sense.
Okay, because what this is saying, I mean, let's go back to the Earth example. So we'll just take my TI-89 here. My TI-89, I toss it upward. I give it some energy. It's not going to get nearly enough energy to escape the potential energy well of Earth's gravity, right? But what this says right here, Schrodinger's equation just says, is that if I toss this up, there is non-zero probability that it will escape Earth's gravity. Not because I'm crazy strong with how I toss it. Has nothing to do with it. Just because of the wave nature of matter. So this is where we start seeing that there are differences. We've already kind of seen some differences, but it turns out that probability is crazy low, like insanely low. But it's non-zero.
But it's possible.
But it is possible.
That's wild.
Right? Like it's possible that if I let go of this calculator, that instead of falling down, it starts going upward. I would be shocked as hell if that happened. Right? And in fact, I hope to God that when that happens, well, here we go. We'll run that experiment. Ready? Maybe we'll get lucky. Let's try again. Oh, okay. I just hope to God that when I do that and it like launches up, it's being recorded on Zoom or something, because no one will believe me otherwise.
So it's funny that it made me think just now, like, could you imagine telling Isaac Newton this stuff?
So, hey, Newton, I know you got this grand idea about apples falling on you and all that, but what if the apple actually fell upward? Yeah. No, because it doesn't, saying that it's possible isn't really fair. I mean, because yes, it is possible, but we're talking about such a minuscule, so unlikely not going to happen that it's never going to happen. But we can't say never, because maybe it's that 1 in 500 million, bajillion, quadrillion, zillions, whatever. Maybe we got lucky. Right? Just like if I take my hand and I slam it against the wall, there is a non-zero probability that my hand goes through the wall. And not because I break the wall, right? I can just be like knocking on it, right? Knock on the door. There's a non-zero probability that my hand shows up on the other side. That would be equally freaky. But the math suggests that it is possible. And obviously, it depends how close your E is to your U naught. The closer you are to U naught, the more likely that is to happen. The higher these exponential things get up. Because, and again, that should make sense. If you're on the verge of having enough energy to get out, you should definitely be more likely to get out than if you're far away. Right? But Schrodinger's equation definitely suggests that it is possible to escape out of a potential well even if you don't have enough energy. All right, well, I know that that's unsettling, but if this wave nature stuff is right, and everything suggests that it is, there is non-zero probability that you can actually be outside. Okay, so there's that example with a finite finite potential well. So let me show you another situation. And this one, we have lots of evidence for. But this time, let's put in a potential barrier. So instead of it being a well where we're trapped between some areas of high potential, we just have an area of high potential that gets in the way. So what I mean by that, if we come back to, this is going to be our potential energy, and this is our position. What we're going to see now is a region of 0. And then some kind of barrier, and then back to 0. So the way to kind of interpret this graph, or to think about what it means, is that except for in this region right here, and let me, excuse me, I'll even say we're going from 0 to L. So with the exception of being between 0 and L, our particles are free. Okay, so our particles are free to do whatever they want. They're just living their lovely particle wave duality life. But somewhere in here between 0 and L, there's a region of high potential energy. Okay, so if we could think of this from Schrodinger's perspective, on either side of the barrier, we get U equals 0, which just means we're going to get good old sinusoidal graphs. We're going to get sinusoidal probabilities. It's going to be what we would expect it to look like, right? Where nothing's going on. Okay, but then on the inside, if we kind of do the same thing, we're going to get a U minus or U naught. Let's say that this is U naught. We're again going to get that U naught minus E. And depending upon its sign, plus or minus sign, we're going to get the two different forms. So if E is bigger than U naught, if our particle has more energy than this potential energy blocker, what we're going to see in this region is, again, sinusoidal. It's going to behave as if that was never there in the first place. So what gets interesting is that when E is less than U naught. So let's say that this is our E level. So we're below U naught. All right. So this leads to a three-parter in terms of trying to get the graph of this, or trying to determine psi, and then its probabilities and all that. Okay, so before we get to zeros, we're just cruising out here. It's business like usual. We get a sinusoidal for our psi. All right. Inside here, we get exponential. And we get decaying exponential. And then outside, we get sinusoidal again. So what that would look like would be something like this. So this green is going to be psi. So you're going to get some sort of a sinusoidal thing here. Yeah, that'll work. And then in here we get exponential. No. Let me move this up a little bit. I'm going to give it bigger amplitude just so we can see what's going on better. Okay, so there's that. And then in here, we're going to get decaying exponential. And then as soon as we get outside, we get sinusoidal again. So this would be a graph of psi, depending upon how everything kind of worked out. But we go from one sinusoidal to another sinusoidal. The one on the outside has smaller amplitude, but it's still sinusoidal. All right, now I want you to think about what the implications of this are. So this green graph is the wave function for a particle. And this particle started over here on the left. It's just cruising along and it comes to this barrier. But the math suggests that this particle does have some of its wave function outside, which means that there's a non-zero probability that we're going to find this particle on the other side. And this is totally Schrodinger's cat. This particle is on the left of the barrier and it's on the right of the barrier at the same time. We're only going to know which side it's on when we observe it. That's when it's going to decide where it happens to be. And it actually could be within the barrier too, right? But in general, the probability of being in that barrier is pretty small because the 0 to L width compared to the rest of whatever is kind of on the small side. Okay, so what this means is that if we're just a free particle doing our thing and we come into contact with some sort of a potential barrier, something that's making us not want to travel through, be it gravitational potential energy, electric potential energy, like it doesn't matter. There is definitely non-zero probability we're on the other side. I'm sorry, say that.
How was this Schrodinger's cat again?
Okay, because Schrodinger's cat is alive and dead at the same time, right? It's alive when the particle has not decayed. It's dead when the particle has decayed. And it's the same kind of thing. This particle is living on one side of the barrier and on the other side of the barrier. I mean, suppose we just say the barrier is decayed or not. It's got two different existences. One is on the left of the barrier and the other is on the right of the barrier. And they are both happening simultaneously. But
Crazy.
when we observe it, then we're going to know, because like we look for this particle, right? And we go, oh, here it is. It made it past the barrier. But it was that moment of observing it that made it decide to be on the side, as opposed to being on the other side. So that's what I meant by it's Schrodinger's cat. It's living two different existences. It's living on each side of this wall at exactly the same time.
Crazy.
It is
Crazy.
And this definitely doesn't fit well with classical, right? Classical mechanics would say, if you don't have enough energy to get past that potential energy barrier, you're not making it to the other side. You're going to be stuck over here on the left. End of story. No discussion. However, in this quantum world, oh no, there is the possibility that you're on the other side. The closer your E is to U naught, the more likely you're going to be on the other side. But even there in classical, nope. Like if it takes 100 joules to get past this barrier and you only have 98, tough luck. Right? That's what classical physics says. But in quantum physics, you know, close enough is close enough. It is the possible, there is a possibility that you make it through. So this right here, we call this tunneling. That's the name for this. Because the particle is tunneling through, it's digging through this potential energy barrier. And how likely it is to make it through depends on a couple of things. So let's just talk about what makes something more likely to tunnel. So we'll just start making a list here. So you're more likely to tunnel if, all right, so what are some things that might make it more likely for a particle to make it to the other side? And when I say more likely, I mean make it so that the wave function on the other side has greater probabilities, bigger amplitudes. What do you guys think? What might make it more likely?
If E is greater than U.
Okay. So how about I'll just put bigger E. If it's greater than U naught, that's even better. But regardless, as long as if E is bigger, we're more likely to make it out. All right, what else? What else could make it more likely to get past a barrier?
If it was already in that barrier to begin with.
Okay, that is definitely true. But let's go with the, no, we're on one side. We're coming up to the barrier. How about this? What if we have smaller U naught? Meaning, what if that barrier's not as tall? Does that make sense?
Yeah.
Right? So if U naught is smaller, we're going to be more likely to make it through. So we can kind of combine these, bigger E, smaller U naught. Really what we want is for the difference in E and U naught to be smaller. Whether we make that difference smaller by decreasing U naught or increasing E, either way, right? The smaller that difference, the more likely we're going to make it through.
That makes sense.
Okay, so yeah, that should make sense. And then one other thing, and sometimes people don't think about this, but as soon as I put it up there and talk about it, you're going to go, oh yeah. How about it's a thinner barrier? Hey, look, Victor just said, oh yeah. Thanks for that, Victor. Appreciate it. But I think about it. So this barrier, now realize it's not necessarily a physical barrier. It may not be an actual like wall or something, but it's a region where we need a lot of energy to make it through. Okay, if it takes a lot of energy to make it through, if that barrier is really thin, it's a really short amount of distance where we need to be able to get past it, we're going to be much more likely than if it's really thick. Right? So if we can take that barrier and make it thinner, No, that would help as well.
So is that like saying, like, instead of going from an s orbital to a d orbital to going from s to p?
Sure.
I think that was correct. I don't know.
I believe it goes SPD. Yeah, I think you're right. Um, so it's like that same, like, okay, let's think like an electric field. Let's say there's an electric field that's creating some huge electric potential, and you were to fire electrons at it. It's more likely that an electron is going to make it past that potential difference if it's thin than if it's really thick, right? Because as it's going through, it's having to fight it, lose energy. It may not make it all the way out, where if it's really thin, it could cruise on through. So this is something else that will make it more likely for an object to make it through. All right, well, the physicists that played with this came up with what they call the transmission coefficient. Let me write this guy up here for you. So okay, so it's the transmission coefficient, and what it is, we use the letter big T for it. And before I give you the formula, let me just tell you that what it is this is the probability of tunneling. So what's the probability of making it through? Okay, so T equals 0 means you stay on the side. And T equals 1 is you go to the other side. So if big T is 0, you don't make it through, ever. If big T is 1, you always make it through. You always go to the other side. So usually we get a, usually we'll get a number between 0 and 1, obviously. But the closer it is to 1, the more likely you are to make it to the other side. Okay, now, this is an approximate. We use an approximation for this, but it's approximately equal to this. And I'll explain what everything is here in a second. So we get GE to the minus 2KL. And L is the L that we're talking about, which is the width of the barrier. So you can see as L gets bigger, this probability drops. As L gets smaller, this probability goes up. Okay, this guy K, this is 2m times U naught minus E all over H slash. You may remember seeing something that looked like this. This comes from the derivation of the psi from the differential equation. All right. But again, notice what happens here if these two get closer. Right? If these two guys get closer, this gets closer to 0, which makes this closer to 1 times G. But that's going to increase this. So that's where this bit, the difference between those getting smaller, adds to the increase.
What if the energy of the particle is the same as the energy needed to go over?
Okay, so if that's the case, we can still calculate what the transmission coefficient is going to be. Well, okay, if it actually is equal, you can't use this formula. because the G is going to end up being 0, which is not correct. So for this formula, this is for when U naught is bigger than E. All right, so if U is actually equal to E, go back to the differential equation. Let's bring up Schrodinger's equation again. So you have all that garbage, right? Stuff times psi double prime plus U times, oops, not E, U times psi equals E times psi. So if U is equal to E, those go away. So you get psi squared equals 0. So what kind of psi do you get?
Just a constant.
Not a
Or
constant.
just an X for whatever your
Yeah.
variable is.
So you get a linear. So your psi is now linear. So your wave function is linear. And so your probability is a quadratic. And you have to adjust your quadratic so that it gives you 0 sorry, gives you 1 when you integrate over the whole thing. So you'd have to scale it appropriately. But all right, so in that case, your wave function looks like a quadratic. Well, that just means that within this barrier, so in this region, it looks quadratic instead of exponential. Okay. Whatever. It's just going to end up linking whatever wave out here to wave on the other side. It just makes it so that the probability of being on the other side is much bigger. So you don't lose as much, like when I drew these and I had the two amplitudes and they were like insanely different. If U is equal to E, they get closer to each other. They're not identical because there's still the possibility it doesn't make it through because of the thickness of the barrier. If it was infinitesimally thin, then we're good to go for sure. But we're not going with infinitesimally. We're saying that there is a region where there's thickness. But we can totally run the numbers for any situation. You can just always come back to Schrodinger's equation and do it. But let me come back here and just so you know what G looks like. G is this really funky thing. It's not the gravitational constant. But it looks like this. So that's just a multiplier that we put onto this exponential piece. So you can put this all together and get your probability that it actually passes through. So let me show you an example. Let me actually run some numbers for you so you can see how we do this calculation. And we can actually get a probability so you can actually take that number and think about what that means in terms of the likelihood. So here's an example. Let's say that we've got an electron with E equals 2 electron volts. Comes up to a barrier of height 5 electron volts and a thickness, let's say, of 1 nanometer. So our electron is just doing its thing, comes up to this potential barrier that's got a much greater energy than it, right? 2.5 times. But it's thick. It's about 1 nanometer. So you guys have an idea of nanometers a little bit from wavelengths of light. But that's about roughly 10 diameters of a hydrogen atom, plus or minus. Okay, so if we had 10 hydrogen atoms and just linked them all together, that's the distance that we're talking about. So not very big. It really isn't very big, but there it is. So let's see if we can calculate T, and we'll talk about what that means, the consequences of that. All right, so let's go and punch all this stuff in. So G is going to be 16 times 2 electron volts over 5 electron volts times 1 minus 2 electron volts over 5 electron volts. And I'm pretty sure that that's 3.8. So it's dimensionless. It's just 3.8. Okay, so then K is going to be the square root of 2 times 9.11 times 10 to the minus 31 kilograms. That's the mass of the electron. And then we have our difference in our U and our E. So U minus E is going to be a positive 3 electron volts. But real quick, we should probably convert that to joules. Because if we've got kilograms, we need our energy in joules. And 1 electron volt is 1.6 times 10 to the minus 19 joules per electron volt. Let me clean that up a little bit. Okay, so there's our 2m and the difference in our energies. And then, of course, we're going to divide that by h slash. And h slash is around 1.055 times 10 to the minus 34 joule second, not per second, joules times seconds. Okay, so you run the numbers on that, and K is around 8.9 times 10 to the 9th per meters. It's meters to the minus 1 are the units. Okay, so let's take those and put them into our transmission coefficient formula. So T is going to be approximately equal to 3.8 times e to the minus 2 times 8.9 times 10 to the 9th times L. And so we are going with 1 nanometer. So that's going to be 1 times 10 to the minus 9 meters. So again, notice the units cancel and we get dimensionless. But this is around 7.1 times 10 to the minus 8. All right, so that's your probability that this electron is going to make it through this 1 nanometer barrier when its energy level is 2.5 times, or when the barrier has a potential energy of 2.5 times that of the energy of the electron. So this is not likely, but it's not 0. And in fact, like let's say we had an electron gun that's firing electrons at these. 1 out of every 10 to the 8th, so 1 out of every, what is that, 100 million, would make it through that barrier. And I know that doesn't seem very likely, right? 1 out of every 100 million. But I mean, suppose this was a real life thing, and maybe we're talking about, particles that are getting bombarded by the sun. Yeah, we get hit by that, like there's tons of those things. So it is possible that stuff is going to make it through. Now, here's what I want to show you. This is pretty crazy. Suppose we cut this in half. So instead of only being being a thickness of 1 nanometer, it's only going to be half a nanometer. So we'll just cut it in half. Check out what this does to our odds. So notice that nothing here changes with K. Nothing changes with G. The only thing that changes is this gets cut in half, right? So now this is 0.5 times 10 to the minus 9. Well, if you run the numbers on that, you get 5.2 times 10 to the minus 4.
So it almost gets cut in half as well.
Oh, more than getting cut in half. Right? Getting cut in half would make it 3.5 times 10 to the minus 8. We actually cut that power in half. So now instead of 1 every 100,000 times, this is happening 1 out of every, or 100 million times, sorry. Now it's happening 1 out of every 10,000 times. It's 10 to the 4th, so 10,000 times more likely to happen. So this thickness of the barrier plays a huge part in how likely something's going to make it through. And in fact, it plays even a bigger role than the difference in the energy. If we had doubled the energy of that electron, so it had 4 electron volts instead of 5, we wouldn't have gotten that big of a number. It would have increased, but I don't think it would have been on the order of 10 to the minus 4. So thickness of the barrier is probably the most telling thing for when something will make it through. All right, so
Kind of shocking, honestly.
it is. I mean, you would think, well, geez, if our energy is really close to that of the potential energy, we should be able to make it through. But okay, if it's really close, but it's a huge thickness, it's still going to be tough to make it through. Right? Think about this. Suppose that you're walking in mud, right? And think of the height of this barrier as the how deep the mud is. If you have to walk through mud that's up to your chin, that's going to be really tough, right? If it's only up to your knees, that's going to be easier, and you're going to be more likely to be able to make it through. Okay, but let's say you're in up to your knees, but you got to go 10 miles. That's going to be a lot harder than having to go 100 yards. Right? And so it's kind of that same idea. Like, think about this barrier as, I mean, it's really pushing back on you. This barrier is really pushing back on this electron. And so if the electron can have less of an amount of time where it's getting pushed back on, the more likely it is to make it through. So, but yeah, it is pretty interesting that thickness plays such a big role. All right, now I told you that we know for sure that this is a real thing, that barrier tunneling is a real thing. And it's not because sometime I put my hand through this just magically. Like, can you imagine if, oh no, I should do it. We'll do like a Chris Angel mind freak kind of thing, right? It's like, oh look, I made it through my hand, right? So it's not because of that, because that doesn't happen. But we actually do see tunneling for realsies, and a great example is with nuclear decay. Now, we'll talk more about nuclear decay later. Like, we'll really talk about it and what's going on. But one example is what we call alpha decay.
Real quick,
Yeah,
theoretically, if I was moving with enough kinetic energy, I could go through a wall without, hurting myself.
without breaking the wall. Yeah,
Yeah, or myself.
yep,
Crazy.
yep. Which, I mean, basically what that tells me is, well, this always brings me up to Nightcrawler from the X-Men. I don't know if any of you guys know who that is, but Nightcrawler can teleport. If he can see, or if he knows what the surroundings are, where he's going, he can just teleport there. So this tells me that Nightcrawler has the ability to affect his wave function. And so he can change his wave function so that he can tunnel through the barriers. So yes, Ralph, that is who we're talking about, the German guy, who I believe is the son of Azazel. But Azazel can do it too, right? He can just teleport. So any mutant who can teleport, clearly they have the ability to alter the wave function of all of the particles in their body. And this is where it really comes down. Like, think about this. We're just talking about for an electron going through a half of a nanometer wide thing, and we saw that it's a 1 in 10,000 chance. Okay, well, that's going to happen. But think about if I'm going to take my hand and try to walk through the wall. Every single particle that makes up my hand has to tunnel at the same time.
No way.
Yeah, the odds are very much against you. Because I mean, think about, we did this for an electron. Don't know if you remember that formula. That formula had a mass in the square root in the top that went into the exponent. You increase the mass of an object, you're decreasing the likelihood that it makes it through. So think about the particles in my hand that are not electrons. Even if we just went to, okay, well, every proton and neutron we're going to treat separately, they are significantly more massive than electrons, which means they are significantly less likely to tunnel through. So if anything, I'll get some electrons that make it through the wall, right? Electrons that come through the computer screen, but probably not any protons or neutrons. Yeah, okay, so that's an issue there. But anyway, I'm convinced that that's what that mutation actually is their ability to alter the wave functions of the particles in their body. That's pretty cool mutation, in my opinion. I'm probably one of only a handful of people in this world who, when they watch things like the X-Men, think about the physics behind it and like what those mutations actually do and all that. So yeah, I'm probably one of the only people in the world. Well, think about this. So think about Cyclops, the one with the that basically shoots laser out of his eyes. How crazy is that? So somehow his mutation was he's created a, well, let's just say a power source that's constantly allowing particles to get excited so that then they can get unexcited and release photons, and enough photons that are, well, they're all exactly the same wavelength, so it's clearly there's a unique energy gap. But to get that volume with that much power, dude, that's crazy. And don't get me even started on, like being able to turn your body into metal and all that. So flying, Ralph, I don't know, you just develop different muscles that allow you to um, create enough speed to create enough lift to allow you to fly. But that's going to be a lot harder for bodies like ours because they're not designed for flight like birds and all that. As opposed to levitation, they're affecting the gravitational field around them somehow. They're producing maybe like anti-gravitons that are canceling out the gravitons from the normal gravitational force. Or unless you're Magneto. Magneto levitates because he's creating a magnetic field that counters, the magnetic materials that are in the earth or whatnot. So so I'm saying Superman doesn't actually fly, actually. Here's what I think happens with Superman. Because he's used to a much stronger gravity, he basically just jumps really, really high.
So he falls with style.
Yeah. So he just like, okay, well, I want to go over there. He just jumps sufficiently so that he ends up landing over where he wants to be. It just looks like he's flying. But I don't know. I mean, I guess he does change course somewhere in the midst of it. But Superman's DC. That's not even like real comics, right? If it's not Marvel, no, not a joke. That's why I said hovering. You're affecting the gravitational constant or the gravitational field. So I don't know how Superman does it. I'm just saying mutants because of whatever their mutation is. They've been able to develop those powers. So I'm telling you, X-Men is so much better of a world to have because when you just open it up as there are random mutations that give you these powers, it's you can create anything you want, right? As opposed to Superman being an alien, and the reason he's got abilities is because it's a different sun and different gravity. Yeah, that's a little bit tougher to do. But then again, Superman was created in the 30s. The X-Men, I think, were in the 70s, so the world was a little bit different. There's actually a really cool book. If me talking about this makes you kind of like get excited or whatever, I think it's called like The Physics of Superheroes, and it talks a lot about this stuff. There's another one I've read. It's like The Physics of Star Trek. So if you're a Trekker or a Trekkie, there's The Physics of Star Trek, and I know there are like multiple versions of that or multiple in that series where they talk about a lot of the science that would be necessary to do the things you see in Star Trek. And I wouldn't be surprised if there are some more, but those are just the ones that I know of off the top of my head. And to his credit, Stan Lee, who created the X-Men and Spider-Man and a billion other Marvel comics, he was actually pretty decent with his physics. I know that there's one good example they talk about a lot is Spider-Man comic where the girl is falling and Spider-Man goes and grabs her and then slings a web to stop her from falling, and she ends up breaking her neck. because of the whiplash, because of the impulse from the force of getting stopped by the spider web, right? So when Spider-Man goes back to get her, he's like, oh my God, she's dead. Her neck snapped because of this. And it's like, yeah, because Stan Lee knew his physics. Anyway, I digress. Good job, guys, by the way. What was that, a 15-minute conversation on the physics of superheroes? But let's come back to alpha decay for a second. So alpha decay, here's what's going on for, we'll actually look at the reality of it in a little bit, but here is your nucleus.
Real quick, Peter should have known that because he's a physicist. He studied physics.
Yeah, but he's just a dumb kid.
I know, but he should have known better.
But he's a dumb kid, right? Like, how many of us, when, I mean, what Peter's supposed to be in high school or just after high school or whatever. So, okay, when you're 18, you're not thinking about that, right? He's just thinking about, oh, I'm going to save her and then she's going to kiss me afterwards. I mean, well, who knows if he even gets that far in his thought process, but he's just a dumb kid. These things happen. All right, so alpha decay, nice try, Bradley. I'm not falling for it. I'm going to keep going. All right, so in this nucleus is an alpha particle. That is fair, Ralph. That is fair. He just put something about how Peter actually thinks about how hard to punch sometimes. So it was a lapse of judgment. How about we'll just chalk that up. So in the nucleus is an alpha particle. We'll talk about what the alpha particle is actually made of. And it's not that there's actually this alpha particle, it's just portions of the nucleus. But this alpha particle lives in the nucleus. But there is a potential barrier for this alpha particle. It's the strong nuclear force. So we haven't really talked about this, but there's a force called the strong nuclear force that basically binds all of the elements in the nucleus together. In order for this alpha particle to escape the nucleus, it would have to get beyond the region of this strong nuclear force. So if we were to draw a graph, and this is going to be R versus potential energy. What you're going to see with this is that there's some strong potential energy that's holding it in. In fact, I'm going to call this negative. It's going to be negative for a little bit. And then we're going to get to the point where it can escape. And beyond that, it does an inverse square with R because now there's, the electrical repulsion and stuff like that. But it looks a little bit like this. And so this is acting like a barrier. Now, it's not a square barrier like we saw before, but it's a barrier. And this alpha particle has energy. So it's going to have some energy level, let's just say, this guy E. And so there is non-zero probability that that alpha particle is going to end up showing up outside of here, where classically it would never leave. It's never going to get outside of the nucleus. All right. But we do know that alpha particles do get emitted. We can measure that. And in fact, when we talk about radioactive decay and we talk about half-life and all that, a lot of those decays are alpha decay, this one where an alpha particle is leaving. And we can even make a number of half-life, right? For how, on average, how long it's going to take for half of them to happen. Well, think about those ones that have incredibly large half-lives. Those are ones whose transmission coefficient are very low. It's not likely that that particle is going to leave. It's not likely that it's going to decay. As opposed to something that's got a very short half-life, those alpha particles are very likely to escape. Why? Well, either their potential energy is much lower, the potential energy of the barrier is much lower, or it's not as thick, or whatever. But that leads to a much higher transmission coefficient, which allows them to escape more. So just the fact that we see alpha decay definitely suggests that there has to be tunneling, because without it, it would never happen. So that's just one more example of evidence that suggests this wave duality, this particle wave duality is real. It exists. And this fairly simple model illustrates it, which again, I think is kind of cool. He says, saying that Schrodinger's equation is a simple model, but it actually is. If you think about it, it's a pretty small, precise one equation that describes all of this. Yeah, that's pretty good. All right, so there's a little bit more about Schrodinger's equation and some of the consequences. I know that we're kind of early today, but I sort of feel like stopping. This is a good place to break. So next time, man, I don't even know what we're talking about next time. I think we're going to start getting into the structure of the atom and actually get to stuff like you know, how alpha particles actually exist and what they do. So that's kind of where we're heading next time. In terms of quizzes, yeah, I don't care. We're not going to do a quiz this week. We'll do another week off. I don't really care. So we'll plan on our next quiz being a week from Thursday, unless that's an exam day. Then we're going to have an exam a week from Thursday. And we'll do a quiz after. All right, but we'll worry about that later. That's not something we need to worry about right now. All right, so with that, I'm going to go ahead and pause our recording and wish you all an awesome couple of days.